Hey everyone, Kevin here. Today we're going to be looking at another AIME problem, this time from the 2002 AIME 2 number 7. Now this question states, it is known that, it gives you a formula, so the squares from 1 through k is k times k plus 1 times 2k plus 1 over 6. Now of course, personally in my opinion, you should already be able to solve the question without using the formula. In fact, you should have the formula memorized because it's a pretty handy tool to kind of simplify a lot of questions and make computation a lot easier. In fact, I guess the first three, what are these called? I forgot. What am I doing? So this of k is are they, that's n. Are they called ring zeta functions if the zeta will be negative? I don't know about that one. Perhaps. K squared is 2n plus 1 over 6. And k cubed is going to be the square of the first one. So that. Okay, so these three you should definitely remember. They appear somewhat often, or they're somewhat used in the AIME and C10. Makes computation a lot easier in some cases, and for problems like these, or they don't give you this formula above. Okay, so we want to find the smallest positive integer k such that this formula is a multiple 200. Okay, so this means that we have k plus 1, 2k plus 1 over 6 is equivalent to 0 modulo 200. Okay. I guess let's multiply both sides by 6. So we get k plus 1, 2k plus 1 is 0 mod 1 200. Okay. So you know what a really stupid method would be? It's to bash out all 1200 residues and see which one works. So of course we're not going to do that. Instead, we're going to split it up into relatively prime products. So you can split 1 200 into, I think it's 2 to the power something, 2 to the power, or okay, it should be 2 to the power 4 times 3, yeah, only 3 times 5 squared. Okay. And thus we can split this this big modular equation into some smaller ones. No, that's not right. Oh, it's 16 too. And 25. Now, why can we split them up into this? Well, we can note that under the Chinese remainder theorem, that this will give a unique solution modulo 1200, at least these three equations. And this unique solution must be 0 because it satisfies all three. So that's basically how you prove it. I guess the converse would be slightly harder. I mean, you can just suppose that one of them differed or something, and then prove that it doesn't satisfy it. Yeah, you can just say, because if, like, say for modulo 3 it was some other a is not non-zero, then k times k plus 1 times 2k plus 1 would not be 0 modulo 1200. Okay, yeah, the same argument. Okay, so basically these two are equivalent, and whenever you have like a product like this in a modular equation, it's always nice to factor it down into these relatively prime products, because then you can just evaluate them in each case and get some restrictions on k, which is what we'll be doing. So let's start with the smallest one. For mod 3, well, mod 3 we can just bash through all three residues. We bash k equals 0 gives, I think, 0 times 1 times 1 is 0. 1 gives 1 times 2 times 3 is 0. Again, we're working in equivalence, modulo 3. And k equals 2 gives you 2 times 3 times 5 equals 0. Okay, so all three work. So mod 3 gives no information. It doesn't give us a restriction on what k cannot be. Okay, so let's go to the second smallest one, mod 16. So for mod 16, we can also bash out all 16 values. Of course, it's actually not needed in this case because, well, we can notice, and of course, whenever you're working through a problem, you should try to notice tidbits like this. Focus at that, like basically 2k plus 1 must be odd, and this like greatly simplifies the question because we can ignore its factor completely. Relatively prime to 16. Then also k and k plus 1 have different parities modulo 2. Basically, one has to be even and one has to be odd. So because 2k plus 1 must be odd, k times k plus 1 is 0 mod 16. So k this if and only if one of k and k plus 1 is 0 modulo 16. And this happens when k is 0 or 15 modulo 16. So the last one, and the hardest one, modulo 25. For mod 25, we can once again notice k, k plus 1 have different parities modulo 5. But 2k plus 1 is kind of the one we'll have to tackle. So I guess there's two cases. Either 2k plus 1 is equivalent to 0 modulo 25, in which case we're done, or it's not equivalent, which means that either k or k plus 1 must be 0 modulo 5. And we don't say it's 0 modulo 25 because this doesn't exclude the case when 2k plus 1 is 0 mod 5 but not 0 mod 25. So we have to be careful here. So either 2k plus 1 is 0 modulo 25, or it's not 0 modulo 25, which doesn't mean it cannot be a multiple of 5. So in the first case, we have k is equivalent to 12 mod 25, and this is fairly simple to work out. In the second case, if k is 0 mod 5, then k plus 1 cannot be anything modulo 25, and we must have 2k plus 1, or it doesn't have to be 0 modulo 5, I guess, if k is just 0, but otherwise it does. So either k is equivalent to 0 mod 25, or 2k plus 1 has to be 0 mod 25, or 5. So basically we're just doing some casework. If k is equivalent to 0 modulo 5, then because k plus 1 can't contribute anything, then either k like kind of takes the entire share, or it splits up 25 and 5, 5 with the 2k plus 1 factor. So k is equivalent to 25 is a solution. And the case when k is equivalent to 0 modulo 5 means that 2k plus 1 cannot be 0 modulo 5, and the other yields no solution. Okay. Now if k is equivalent to 4 mod 5, which means that k plus 1 is 0 modulo 5, we have the same thing. So either k is equivalent to 24 modulo 5, so take the entire 25, or it splits it with 2k plus 1, so 2k plus 1 is equivalent to 0 modulo 5. So in the same manner, k is 24, yields a solution. And the other one, when we plug it in, we get that 4 times 2 plus 1 is not 0 modulo 5, and therefore the other yields no solution. So basically, k is equivalent to 0, 12, or 24 modulo 25. So these are our conditions on k. So k must be 0, 15 modulo 16, and 0, 20, 24 modulo 25. And basically we want to find the minimum positive integer k such that these conditions are satisfied. Of course, now this is just a little casework. We know that both sides cannot be 0. If it is 0 for both, then k is 0 is not possible. Or at least we're kind of excluding like the higher residues, because we assume that there should be one within like the initial residues that actually works. So we're not considering, for example, that k is 16, or no, k is like 16 times 25, for example. Actually, I mean, we can just do some casework, I guess. From here, it's not really that hard to finish the question. The intuition is that one of them should be 0 because we want the lower residue, as low residues as possible. and just try to get a, So you know what, to be more rigorous, I guess, we'll calculate all possible residues. Let's calculate all residues. And this is modulo 400. Okay. So what does, okay, 0, 0 gives 0, of course. I'm trying to think of how to like write this down so it's not messy. So 0, 0, let's do this, goes to 0. 0, 12 goes to, let's see, this is just the messy part, I guess. I think that's 112, but not sure. And 0, 24 goes to, essentially I'm just like computing a bunch of values in my head and seeing which one works. So like 124 is like 25 times 4 plus 24, and that is not a multiple of 16, so we move on to 174, which is not, so 224 is, so it's 224. Interesting how it doubled. I'm pretty sure there's some trick to it, but I'm kind of too lazy to do that. So 15, 0. And of course, this is always nice to kind of double check your answers. So 15, 0 gives you, though it is tedious, must be a multiple 5, so 95, 175. 15, 12 gives you, This is pretty hard, huh? I don't really like doing this stuff. Okay, so it has to be, let's just do plus 1. It has to, it plus 1 has to be divisible by 16. So it has to be odd, for example. So 37, 38 will not work. Plus 50 is 87, 88 does not work. 137, 138. 187, 188, 238. 238, is that it? Or 288. Yeah, I think 288 would work. Okay. So this goes to, okay, this will obviously go to 399. Like this one is not hard. It's just -1 modulo both residues, so it has to be -1 modulo 400. And oh, that's it. Okay, so our answer is, well, 0, of course not. It's 112.